So I'm going to switch. I think I'm about a little over halfway in my talk time. I have about 20 minutes left. So I just want to summarize quickly here some of what we looked at in data-intensive science, give you a flavor for it, what we did in Magellan, and sort of what we are continuing to do here. But some of this work is ongoing, and we are constantly, actually continuously running experiments even right now to analyze some of these things a little better. So MapReduce learning was essentially that they were really useful, very useful for high throughput workflows. They're also very useful when you have a small problem that you're coding up on your desktop and then you want to scale it up to a large number of machines. But they show promise, but their current implementations of MapReduce, or more the commercial implementations such as Hadoop, have gaps for scientific applications. One of the biggest challenges, Hadoop uses its own file systems with HDFS, which is non-POSIX compliant, right? And most of our applications have been written assuming a POSIX file system interface, and it would essentially require rewriting these apps to be able to seamlessly run in HDFS environment. You can still run Hadoop with another file system, but if you really wanted all the benefits of data locality and fault tolerance and everything, you really would need to rewrite your application. Java is the primary language of support, and every time I mention Java, my scientists look at me really strange. So that's definitely not a viable option for most people, especially because they have legacy codes from a number of years with a lot of investment of time and energy that's gone into it. Most of the input and output formats Hadoop assumes is mostly line-oriented text, and I don't know actually many cases of scientific input data sets which are line-oriented. They have blocks of text or they're files that are input, and so you have to develop a lot of extensions in something like Hadoop to be able to support these scientific applications. It's been done. There's some communities, especially like bioinformatics, which has been putting in more effort into this, but there's significant learning curve here. The streaming mode, which is where you can take an existing binary and drop it into Hadoop and have it run as your map and reduce job, is probably the most viable approach for most of our users, but it's still pretty restrictive because it assumes your input and output come in on standard in and standard out, and so that still involves a number of hacks where you have to have the application pretend like it's you have to sort of stream it in onto disk and then have the application read it again or something like that. So this work was actually published in IEEE Cloud and was presented in June this year. So what we did was essentially took a bunch of data-intensive operations, filter, merge, and reorder is what we picked, and we ran these on public data sets, mostly because it's hard to do some of a more controlled experiment with scientific data sets, and ran this on NERSC Magellan resources. So we used the census data and Wikipedia data and basically developed a set of applications which did filter of the data, merge of the data, where merge essentially grew the size of the data so your output was greater than your input, and a reorder. So reorder is sort of a little bit like a sort. And the data operations definitely impacts the performance difference across these file systems. So if you look at the Wikipedia data here, for about 2 terabytes, you see what our comparison here was looking at saying, can you use Hadoop with GPFS as its file system, and how much performance impact does that have with respect to using HDFS, which is more optimized for these data operations. And what we found was at about 2 terabytes of Wikipedia data, filter pretty much did exactly on pretty much close on GPFS and HDFS. There was really no particular difference in performance, and HDFS actually did much worse than GPFS as we had applications that were writing out more data. And this is largely because HDFS does a replication factor of 3, where every write ends up being replicated on 2 other servers. So there was a lot of network traffic and a lot of network contention as there were a lot of writes being done, and we saw a significant impact on HDFS performance for the more write-intensive applications. So the question was sort of at what point in the write cycle does it make the scalability that comes from HDFS, because it has its own local disk on each node that it can rely on, do better than GPFS. So this graph uses TerraGen, which is the precursor to TerraSort, which is a sorting this, and TerraGen basically generates a lot of data. Essentially, that's what it does. So we did a graph with increasing the concurrency and just keeping the data size same, and we see that somewhere between 1200 and 1500, 1200 and 2000, you'd see that HDFS would start doing significantly better. This was just an extrapolated graph, but we have more data that shows that this is mostly true for most of the applications in terms of concurrency. There's always the question of how many maps per node and stuff, and so we did rough estimates here on that. So the next thing we did was to say, so we sort of had an understanding of what kind of concurrency it was okay to run GPFS with. So we sort of also wanted to understand how much overhead there was from streaming. So we wrote a very simple, the filter application also in C. So if you look and then ran it on a single node, so the graph that you see on the left essentially shows you the comparison of C versus Java, and C is definitely a much faster code than Java at these sizes of data, and probably all sizes of data actually. And then we put the C code as a streaming app in Hadoop and measured the Hadoop native Java app. And we see that both the C and Hadoop native at 0.1 terabytes essentially does the same, which basically means that the advantage that the C app had of being faster was pretty much wiped out as soon as with the streaming overhead. And as the file sizes increases on the x-axis, you see that the gap starts increasing and the overhead from streaming starts showing up. So I seem to be doing this trend where I always show you first what is bad about the particular technology. So I showed you what was bad about virtualization, then showed you BLAST. And so keeping with that trend here, the question is, so where does Hadoop and HDFS do better? So HDFS does significantly better when you have a large volume of data you're reading. So if you have a read-intensive application and you have a large amount of data, like think 2 terabytes or 3 terabytes of data, then your HDFS will do significantly better than GPFS. At that point, you reach a point where the scalability of HDFS far outweighs the GPFS, what you can get with GPFS, and also you have the advantage of data locality kick in. So the application is basically going to be scheduled in such a way that it can benefit from its local copy of the data. The other one that is here is replication and data locality, where we said, so I had my intern, I think he probably went crazy with my instruction, and I said, you need to show me a graph where it shows that data locality matters, right? So, and how much does data locality matter in this? So he came up with this graph where he basically was running different replication counts on the same amount of data and running these apps. And he first, I think, ran up from 1 to 3, and basically there was hardly any difference. And so as he scaled up the replication, though, you could see the data locality effects becoming more clear when you went from 2 to 5. So the graph on the left shows it for filter. When you come for the more reorder type applications where there's a lot of writes being written, the write dominates the cost of the performance so much that you don't actually see the benefits of data locality as much. There's a little bit of benefit, but it's not as much here.